Okay, so we're going to enter into the secure aggregation session. The first speaker is Harish Karthikeyan from JP Morgan AI Research and AlgoCrypt COE. And Harish is going to be talking about the one-shot private aggregation with single client interaction. So the floor is yours.
Okay, so thank you for the introduction. So this is joint work with Antigone, where we talk about open one-shot private aggregation for secure aggregation with single client interaction. You might have to click the... perfect. So this is a big title. I'm just going to take it piecemeal. And federated learning, there's been a lot... Wrong direction. Okay. Federated learning, there's been a lot of speakers who have spoken about it, so I'm just going to keep it really moving. But the idea is essentially there's a model that I want to train with the help of a server. The data is to be held only on the client device, and the implicit hope is that holding the data only on the client device essentially protects the privacy of the data. So this was at least a theoretical spirit in which this was introduced. So this is how federated learning typically works. I have the server that trains a global model. So that's the green one. It sends it to the various clients. So the clients are now deploying the global model. So now the client has the model and it can train it with the local data that it holds. So as a result, it produces a new model, each with different color, because obviously the data changes. And now the server essentially gets each of these local train model updates. And what the server does is aggregates it and uses it to update the previous global model. So this is done iteratively. And eventually, the users again receive the new blue model. And this can happen over and over again, until some kind of model convergence is achieved. And so this is what typically the population size and the devices that are chosen. So while there might be a large number of devices in each iteration, we do focus on a subset that's randomly chosen typically. And this is from the work to sort of formalize one of the open problems in federated learning. And this is not a theoretical exercise. This is also something that's industry interested. Though, I mean, I guess there's been some dispute on whether Google is still using Gboard or not, federated learning, but anyway, this was one of the motivating applications. So this is not purely a theoretical exercise. There's still enough meat in it for the industry to be interested to deploy it for practice. And the problem here is that there's a big privacy concern. And repeated works have shown that, there's been a long line of work that has shown that even if I get just these little updates, I can do a model inversion attack and somehow get the data that the model was trained on. And I'm just citing two of the works. There's been a long line of work that has used this loophole to find attacks. So therefore, I'm actually going all over the place. Give me a second. Yes. So now the goal is now, can the server somehow just compute the aggregate where the clients now send the model updates in an encrypted format, but you still want the functionality to be preserved, which is that the server gets to at least aggregate it. And this brings us to the problem of secure aggregation. So in secure aggregation, the goal is somehow the server only learns the final output, which is the sum, while ensuring that all of the operation is happening over encrypted data. And you want the privacy of the client-held model update to be while preserving the functionality. So if you take a look at what aggregation is, you can think of it as a big blue box. I press it. Each inputs are given from the client. So X1 through X5 are client-given inputs. I click this button, great, and I get an output. So this is sum. So this is aggregation. This is basic math at this point. But what do I do when it comes to secure aggregation, right? And in secure aggregation, typically what happens is that each client samples a mask. So now I just mask my own input. So client I does xi plus mi, where mi is some mask value. So now if I click on this blue box, I don't really get the sum. I get the sum of the inputs plus the sum of the masks. And the security comes from the fact that now there's enough masking value that I choose with enough randomness that the inputs are hidden. But then what the server needs for functionality is that somehow it needs to know the sum of the mask. So now I'm going to give you a very simple protocol, and this is not something that's original, as in this is not something I'm proposing. It's been known in literature from the work of Elaine from NDSS 2011, I believe. So this is secure aggregation, where I want to sum up securely, and where the client sends exactly one message. And this is secure aggregation. It's like where I'm now going to tell you somehow from there's going to be the masks value that are dropped from the earth, from somewhere in the ether, that it sums up to 0. So now really what happens is that the output is x1 through x5, because now I know the sum of the masks is 0. But this is, while simple, there are two underlying issues, which is how do I generate these masks? So if you look at the long line of work that's called private stream aggregation, the assumption was that there was a trusted dealer that sums up the that sets up this mask such that they always sum up to 0. But the bigger problem is, what if somebody does not participate? I know that the sum of the masks is 0, but if someone does not participate, the math fails at this point. So this is what we come for secure aggregation for federated learning, because it's assumed that a lot of these devices are really computationally and communicationally constrained devices. So it's not possible to expect that a client always participates. So therefore, you really need to come up with a protocol that can handle dropouts, which is when a client does not participate in an iteration. So this is a brief survey. I mean, note that this was originally designed for also for people who are not cryptographers. So I've tried to keep it a little very, very superficial, because, and this is something that really captures a long line of research, which is that there are 3 phases, right? So one is the setup phase, and this is the phase that really deals with how do I generate the masks, how do I give the masks out, and all of that part of the puzzle. Then there's a masking phase. This is when the client uses this mask to mask its inputs and send it to the server. And then there's unmasking phase, which is when the servers somehow communicate with clients or among clients themselves to remove the masks. So now this is broadly the 3 phases, but in practice, this involves multiple rounds of iteration, sometimes even between server and the client, sometimes between the clients themselves. And I will survey some of these existing solutions in the next slide. So this all started with the work by Lunowitz et al. From CCS 2017, where they said that this is actually doable. This is actually quite efficient. And they said that there's no setup reuse, but I'm going to do a setup phase in every iteration. And essentially what it means is that I'm going to take a mask and I'm going to secret share the mask with enough people. So that even if I weren't dropping out or if I were participating in either of the cases, there are enough people to help reconstruct the mask. Right? And so during the unmasking phase, server now knows which are the clients that are participating in the iteration. So they are just asked to help, hey, please give me the sum of the masks so that the math can proceed and I can stop bothering you again. So this is the spirit in which Lunowitz et al. Began the work. And then they said, you know what? Every client is talking to every other client. It really is inefficient. It's really inelegant. So let me throw a way in which I can somehow secret share with just a subset. So rather than n speaking with all n clients, now n will only speak with a log n clients, like some neighborhood that is defined by some graph that's generated. Right? So this was roughly the spirit in which this was done. So now the communication and the construction cost has gone from n to now log n, because now the client is only choosing to speak with the neighborhood. And then bottom line is, anyway, even if this is not the case, the setup phase and the unmasking phase requires multiple client interactions. And then there was this big work that said, let's reuse the setup. What if I don't need to invest the effort, because now instead of asking n to speak with n clients or n to log n, can I reuse the setup? And this was shown by MicroSecAg, where they showed that, yes, you can actually do this by reusing setup. But they had this caveat where you require the work the model updates to be small, because you have to eventually take discrete log. And then there's also this work that called Flamingo and Lerner, which does slightly different. Flamingo, on the one hand, said, we will use the same setup across some number of iterations. Meanwhile, Lerner said, at the beginning, every client has to communicate with a fixed committee, a static stateful committee, which gets all of the shares. So that's the difference between the two works. And now during the unmasking phase, I will only contact these committee of users. So now still I'm having a login committee members to help, but the reusing setup actually helps avoid some computation. So now this is where our solution comes in, which we call one-shot private aggregation. So note that the whole work that we've been motivating here so far is that if I were to just do learning in the clear, I get my model, I train the model, I get the update, I send the update. So the client has exactly one interaction, right? Whereas now, if I'm looking at all of this line of work, there's been multiple levels of interaction. And that is somewhat, there's a big delta between what we can do in learning in the clear and what we can actually do when we allow for secure aggregation. And the hope of OPA, that's a mouthful, the hope of OPA is to somehow make it feasible where I'm now bridging this gap. So what do? There's no setup phase. And because the setup phase often degrades very poorly with a number of clients. And now I will use a helper committee very similar to Lerna and Flamingo, and I guess even Willow, where I can now change, but now I can change the committee from time to time. But this committee is the only thing that the client is going to communicate with. So on the fly, this is what the client does. The client sends the mask input to the server and somehow just sends the share of the mask to each committee member. So it's a one shot in that the client wakes up, does everything, sends the communication, and goes off to sleep. So now the committee member simply adds the shares of the mask and sends it off to the server. And then the server can unmask with the help of this information. So pretty much everything is like a one-shot policy in the sense that client sends to the committee and the server, the committee sends whatever it has received to the server, and the server can aggregate. So it's all very nice and elegant. We just need to make sure that a sufficient number of committee members are there to help reconstruct the mask. And this is what we want to bridge, which is the learning in the clear is just one shot. So now we want to bridge this gap. And this is, if you really look at it, the one that comes closest to us is Lee et al., which is Lerna, which is 1 + 1 + 1, where the one is the setup phase where every client talks to the committee members and the committee members are stateful. So we actually reduce that. So we just do it on the fly. So now we also compare with Willow because it's a subsequent work that does something very similar, but yet different. And the idea here is that in OPA, we don't really need a setup where the committee members, I just need to know who the committee members are and I can send the communication out. And there's no sum of key leakage attacks. This is slightly technical, but you can look at the paper. Whereas in Willow, you read the committee members or the decryptors to essentially agree on some key ritual to essentially allow for threshold decryption. And then that is the sense that public key secret key pair is now generated such that the committee of members can somehow decrypt the threshold decrypt. And they also require the client to know the key pair. So somehow there needs to be some bulletin board, whereas we require either a PKI or some authenticated encryption channel to send the model updates, the mask in a secure format. So this is the communication flow of OPA. Actually, as an organizer, I don't know how much time I have, but I'll try to be fast. So the client wakes up, sends the mask input to the server, and it sends the shares of the mask to the committee member. And then every client does it. And then the committee member just waits. Once it receives sufficient number, it communicates with the sum of shares. Now, I've sort of here assumed that eventually everyone receives it. But if they don't, the only additional communication is between the the server and the committee members to find out the intersection of the online clients. So there could be a case where the client sends some inputs and due to network delay, the committee member or the server does not get it. But this is one round trip collection, one round trip between the two of them to agree on the intersection. And the security assumption is that the server can collude with the clients, can corrupt the clients, can corrupt committee members. And you still want the honest users' inputs to be secure. And we also have a stronger security model. What if the server is okay, but all the committee members are colluding with each other? And this is something that previous work hadn't considered. But we also, and the beauty is that the small fix that it takes is actually fixes this problem where what if all of the committee members collude? And our key contribution here, the technical contribution here is that we build it from any distributed key homomorphic PRF, right? And we give instantiations from both class groups and LWR, but we also have constructions from LWE and ring LWE in the random oracle model. And the distributed key homomorphic PRF is not something that's new. It was originally shown that there's a construction from DDH, but then you really need to encode inputs in the exponent, and then you need discrete log to recover the aggregate, which is inefficient. And then there's also construction from LWR that was from Bonet. There was originally Banerjee et al. That showed that this was a secure PRF from LWR. And then BLMR 13 showed that it is a threshold key homomorphic PRF, but there was some gaps in the security proof, so which we fixed it in our paper. And we also give constructions from LWE and RLWE, where the technical detail here is that there's this paper where you need to really use hash function in the random oracle model to sample the Gaussian error. So this is from Akira's on this paper. I don't know where it is, but that's a cute little trick that we can use. And so this is the construction of HOPA, which is pretty much where now I'm assuming I'm now doing this key homomorphic PRF evaluation using my input on the iteration value. This is L. So I'm just masking it with the input X1. And I then share the mask with the committee member here. And I do this for every committee member, every client. And now the next step, now what the server can do is it can simply sum up the masked inputs it receives. So now it neatly separates up into there's two aggregation happening. One is the sum of the inputs and one is the sum of the masks. And now the committee members can really use, I use the key homomorphism, which basically says that if I sum up the masks, it's also key homomorphic PRF evaluated on the sum of the keys. So I can take the summation inside. And then the beauty of the collectors here is that they have, if enough of them exist, I can get the sum of the keys alone for free. This is slightly, here, this is a very simple construction. There are some, the thing is, in our case, we actually give only the partial evaluation on the input. We don't really give sum of the keys. Okay. So this is now, with the sum of the keys, it can compute the sum evaluation of this evaluation of the point L, and it can recover the sum of the inputs. So that's how the correctness you get. So it really works well in the sense that the evaluation and the client's interaction is still all one. So client wakes up, does it, bridging the gap with learning in the clear. So if you get anything out of this presentation, it's that we bridge the gap between client not having to wait, just needs to wake up, participate, send the masked inputs, and that's all it needs. And then it can go to sleep. Right, and we do have benchmarking because, we're trying for security conferences. They like a nice little graph here or there. So we throw in some graphs, still waiting to hit success. But hey, the graphs look nice. Thank you, ChatGPT. So we show that we actually beat all of the existing protocol. And in fact, our server computation time is less than 1 second to aggregate. And this is obviously one. And we also show feasibility result to say that, hey, our accuracy doesn't degrade. So we do some data sets, we do MNIST, we do CIFAR10, we do this, that, all kinds of abbreviation to show that we actually still get some meaningful result, that this is not something that's a purely theoretical exercise. So anyway, the conclusion. I've bored you enough, but we've introduced OPAL, which is the first one-shot private aggregation protocol, bridging the gap with learning the clear. It uses a committee of ephemerally chosen clients to make the transaction, to make the iteration go through. So, but the key idea here is that what the committee members do is strictly computationally weaker. They just add up the keys essentially. And we show that there's a secure extension where even if all of the committee members collude, it works. And we build it from any distributed key homomorphic PRF. So as new constructions are built, you can get from more nicer assumptions, post-quantum security, blah, blah, blah. And we also have this interesting extension where we use zero knowledge proof to show that what if a client misbehaves? What if the client sends inconsistent information to the server and to the committee members? And we show that this actually is very efficient because prior to this, the only known work was Acorn, which has this expected log and round protocol where I keep going down iterations because once I pick a malicious client, a whole bunch of clients might be found. So this can happen repeatedly. So, but whereas we have a one-shot policy, which makes the proof easier. And we want to, future work is also composed with range proofs to show that the inputs that are being encrypted are actually valid. And then we compare with various works, including microsegag, which seems to be the state of the art right now. We haven't compared performance-wise with Willow. We are in the works of implementing it and comparing it. And we don't have any loss in accuracy. We have trained it on some data sets, and it's all on ePrint. And we also have this cute little extension, which is we call the SASH trick, which is to use a seed homomorphic PRG, which can significantly reduce the number of exponentiations. And with that, I guess that's it. Thank you. I can take questions.
Okay, so maybe one quick question.
I mean, that's exactly what seed homomorphic PRG will do. So if I were to do this, I would just mask the seed. Sorry. The question was, why do I really need a key homomorphic PRF? Why can't I just use a one-time pad? I still need to add up the masks, right? So you really need a seed homomorphic PRG to then, because I'm trying to add up the seed on the one hand, like I need to aggregate the seed. I also need to aggregate the mask. So I still need at least one key homomorphic PRF evaluation at that seed point. Like, because I really need to mask the I really need to mask the seed as well when I'm sending it to the collector, right? But I'm secret sharing the key to the committee. And oh, I see your point. Yeah. So rather than using, yeah, sorry. Thank you. Rather than using the seed and then secret sharing all of this, this is much more efficient. But we do use the PRG trick to reduce the exponentiations, which is the seed homomorphic PRG trick, which I think it's a cute little trick which we need to implement, but it will reduce the exponentiations. I mean, we can discuss offline. I mean, any other questions? Oh. So that's fine. So if the client wakes up and sends only communication to the server, then they essentially the way I presented it, it's sort of abstracted. So you need to have the committee members and the server interact one round to establish which is the intersection or which is the online clients over which I'm aggregating. So it's yeah, you essentially just need to take one time. I mean, just I send all of the clients that I'm received inputs from, all of the committee members do it, and then the server also has it. It has to take a big and of it, essentially. And if you suspect that the server is malicious, it's all signed. You can throw a signature at it.
Okay, thanks, Harish. So let's thanks the speaker again. Aggregation for federated learning with input validation.
Okay, cool. Yeah. Okay, so I'll talk about a federated learning protocol with input validation. And this is a joint work with cryptography team at JP Morgan, Yue, Harish, and Antigone. Okay, so let's, how about this? Yeah. So let's do a briefly recap on the background because this is very important to understand like what we're trying to achieve. So in a centralized training setting, so this is like in a traditional setting, all the clients will have some local data and they will send the data in the clear to the server. And then the server collects all the data and trains a model. And then in this decentralized setting or so-called federated learning, like the client will train a model on their local data and then got a local weights, which is depicted as like this green one, yellow one, brown one. And then the client will send this local weights to the server. Sorry. Okay. And the server simply adds them up, just a summation, and to get a global weights. So the point here is that the client never needs to send the data in the clear to the server, and the model the server finally gets is equivalent to the model the server gets here in the centralized setting. So this is the federated learning. And what I just described is one iteration in the training session. So to train a full model, this summation procedure needs to run many times on different sets of clients until the model converges, like this. Okay, so now you know like how federated learning works, but there are two major concerns in this community. And the first one is so-called inference attacks. Simply speaking, here the server observing each individual weight sent by the client. And then now the server can do some reverse engineering on the model and then recover partial information of the client's data. And then the second issue is called poisoning attacks. And this is the issue that arises from the federation property. And this is not existing in the centralized setting. So why is that? Because now the clients become the participants of this federated training. So it can send whatever weights it wants to the central server. And now, because of this malicious inputs, it can cause the model performance decrease or even inject backdoors to the model. Okay, so let's take a look at the first issue. Actually, many works has looked at the first issue before, and they solve this problem using the so-called secure aggregation, which Harris just covered. The observation is that to train this model in federated learning, the server really needs only the sum of the inputs, but not each individual weights. So secure aggregation protocol will allows the server to compute the sum of all these vectors from clients without knowing each vector from the client. So this is exactly like what secure aggregation does, and then it solves this problem very perfect. And indeed, there are many recent works proposed like all kinds of efficient secure aggregation protocols. But in this talk, I want to focus on the second issue. So the second issue, it's not that it's not important, it's that it's actually challenging to solve. So the challenge here is the tension between privacy and verifiability. So if you think about how secure aggregation works, the server cannot know the individual weights from the client. So how can the server check the weights if it cannot see them? So this is the challenge here. And what we achieve in this protocol is we have a secure aggregation. So we preserve all the privacy as before, but we achieve, but we can allow the server to check the inputs. And we have this so-called robustness properties at 3 levels. So first, the server will be able to check if the inputs satisfy some predefined constraints. And often these constraints are L2 or L infinity norms. Of course, these are not like provably secure, but like experimentally, some machine learning people shows that they are sufficiently good to prevent certain attacks. And next, we can detect any misbehaving clients in the protocol. So if there's a client does not follow the protocol, the server will be able to know that like this clients you are malicious. And the last one is actually a strong property. So it means that if any client sends a bogus weight to the server not only is able to detect it, but also it can remove this effect from, remove this input from the sum. So here it means that we can achieve guaranteed output delivery, so the server can always output the model, even if some clients acts arbitrarily malicious in the protocol. And we achieve all of this using only a constant number of rounds, and specifically 4 rounds. And the best prior result, which is a current that Harsh mentioned before, has also achieved these robustness properties, but with number of rounds logarithmic in the number of clients. Okay, so our protocol has 2 key components. The first one is a learning with arrow-based secure aggregation scheme. And this is nothing like super new, like the similar ideas has appeared in like arithmetic garbling, private information retrieval and also like some previous works in secure aggregation. But then with this protocol, we're able to build some zero knowledge proof that is very concretely efficient to have the client prove it submits the valid inputs and it execute the protocol correctly. So let's start with the basics of learning with error encryption. So suppose you have a short key S, the client has a short key S, and the client inputs is a long vector X. And now the learning with error encryption is computed as the matrix A times S plus an error vector and plus X. Here you need some scaling factor here, but I'm omitting it just for simplicity. And then you get encryption of X as Y. So like the length of Y is exactly the same as the length of X. Okay, so what does this encryption bring us? It has this very powerful property called key and message homomorphism. So if I have two clients, so this is client 1, it has input X1. This is a client 2, it has input X2. And now they run this encryption algorithm and get the output Y1 and Y2. Okay, so if we add these Y1 and Y2 together, it is equivalent to encryption of X1 plus X2 under the key S1 plus S2. Okay, so now what we do is we'll just let a client samples this short key S1, S2 locally, and then do the encryption locally, and then send the vector Y1 and Y2 to the server. So the server will be able to get two vectors and the server adds them together. And now, in order to get X1 plus X2, the server need S1 plus S2, right? Okay, what we do is just to have the server and clients run another aggregation protocol to get S1 plus S2. And the point is that because S1 and S2 are much, much shorter than the long vector X1, X2, so this secure aggregation between the server and clients should be much more efficient than aggregating long vectors. Okay, so just to recap, we call this inner-outer paradigm. So the outer aggregation is that each client sends an encrypted vector to the server. This is just a single round trip. And then we execute inner aggregation where the server and the clients run aggregation protocol on the short seed S1, S2, and so on. Okay, but now I want to say that this protocol is not the fastest secure aggregation protocol. So why we're doing that? The reason is that this enables fast zero knowledge proof on the vectors and how the client execute the protocol. So if you think of how the encryption is done, it's just vectors additions, and you want to prove some actual properties on the vectors. So because of this, computation locally is very, very simple. So it enables us to build some zero knowledge proof on top of that and make this zero knowledge proof fast. So in this talk, I'll just focus on how we reduce the cost for proving L infinity norm on a long vector. Okay, so let's say we have a vector of length big L. You have some numbers. And now if we want to prove that this vector satisfies some defined constraints in machine learning, let's say want to prove that each component is smaller than the value B. A naive approach is just, like everyone knows bulletproof. So naive approach is that you just invoke a bulletproof protocol on each component of this vector. So if you, like in a little bit more detail, if we want to have a bulletproof for the bound B, then the proof size for each component is log of B. And if you have a length L vector, then the proof size is going to be L times log B. So that means that when the client sends like the encrypted vector to the server, the client also needs to send L times log B for the proof. And this is not communication efficient. And what we achieve here is that using some tricks in some like publicly verifiable secret sharing paper, we can reduce its cost to log of L times B. So here we just move this L inside this log. And this is pretty efficient because like log of L is much, much smaller than L. Okay, so just to summarize, this protocol at high level works as follows. So each client, they will signpost a random short key S, and then encrypt the vector and send the encrypted vector to the server along with a short proof. Now the server will check all the proofs, and if this client proofs fails, it will just kick out this client encrypted vectors out of the sum. And then the server will add all the sums up. And then finally, the server and the clients will run a protocol to decrypt the final sum. And this is the inner aggregation I mentioned before. And this inner aggregation is done on a short vector S, so it should be very efficient. Okay, this concludes my talk, and I'm happy to take any questions.
Any question from the audience? Okay, so since we are running out of time, so let's move to the next speaker. So thank you, Yipin. Okay, so next speaker is Bayu Lee from Google. And Bayu will be talking about Willow secure aggregation with one-shot clients.
Okay, thank you for the introduction. Okay, so I'm going to talk about Willow, so our new secure aggregation protocol with one-shot client. So there could be some overlaps with the previous two talks, because this is like kind of like a very active area. This is a joint work with my colleagues James, Adria, Mariana, Philip, and Pierre. So okay, so as in the previous two talks, we are interested in the following problem. There's a single central server, and there could be like a many big clients. So for example, your mobile phones. And each client has a potentially long vector, and the server wants to learn the sum of all those vectors. And this is a typical, like a crucial component for building federated learning and analytic applications. So as you've seen in the morning and in the afternoon talks, the server, for example, you can use this secret aggregation protocol to train a model in a distributed fashion. And also you can collect, for example, some very interesting metrics, for example, who is the most popular artist. So because all those inputs are privacy sensitive user input, we want to build a protocol like a large scale MPC protocol in the privacy preserving manner. So specifically, we consider in this work, we consider the server could be malicious, and a fraction of the clients could also be malicious. Okay, so formally speaking, we are thinking about the following functionality. So the clients will provide input xi, so those are vectors. And the server either learns the sum of all those vectors, or the server learns nothing if the protocol aborts. The malicious server can drop out a certain honest client before receiving the output. So for security, again, we are thinking about potentially malicious server, and also a fraction of the client could be malicious. So in this specifically, we consider n-1 out of n clients could be malicious. And for the security, we want to make sure that the adversary does not learn anything beyond the output of the functionality. So some attacks or like orthogonal to this work is, for example, we do not consider an input poisoning attack in this work. So as in the previous talk, we can typically just validate the input to mitigate such that attacks. And also we are not for like severe attacks, maybe we can use differential privacy to mitigate those attacks. So we are not considering those attacks in this work. as Harish already shown, so the original secret aggregation protocol uses the following structure. So every client typically just has a self mask. Then also each client has a pairwise mask with its neighbors. So the client masks their input, and the server learns the mask the aggregated mask input. The pairwise mask will cancel, and the client will help the server to remove the aggregated self mask. So as in the previous work have shown, we can reduce the client communication by just use a small neighbor for each client, but still the client needs to interact with the server in order to help the server to learn to remove the contribution of the drop-off client, and also help the server to reconstruct the mask. So because communication is expensive, especially we don't want the client to waste their energy to wait for in multiple rounds to finish the protocol. So there are also protocols like Flamingo or Lerna. So they use a committee to help the server to reduce the client interaction. So in those protocols, the committee can typically be reused across multiple sessions. So still, the committee in those works are kind of expensive. So because they either require a PKI, or the committee itself is expensive to operate because they require some synchronization point. So the ideal properties we want to achieve is the following. So we want the clients to be just one shot. This means that the clients, they can just show up and submit their contribution, and the clients are done. And for the server, we don't want the clients to, we don't require the client to use heavy infrastructure such as PKI. And the server collects the user input, collect the client input. And after the client submitted their contribution, the server will just operate with the committee to learn the aggregate. And also we want the committee to be really lightweight. In particular, we want the committee work to be independent of the input length and also independent of the number of clients. So with this, I'd like to introduce Willow, our secret aggregation protocol. Let me give you an overview of our protocol. So the starting point is to use homomorphic encryption to aggregate client contribution. So this is like a trivial application of additive homomorphic encryption. So the problem with this kind of protocol is that the additive homomorphic encryption is implemented by the committee, and the problem with this is committee needs to the committee work is depends on the length of the input. So in order to reduce this communication cost, we use 2 layers of homomorphic encryption schemes, as just in Armadillo in the previous talk. We use the first homomorphic encryption scheme is the K homomorphic encryption scheme, and for this scheme, every time the client will sample a fresh key, and then the client will use the additive homomorphic encryption scheme, the second HE scheme, which is implemented by the committee. The client use the AHE to encrypt not their input, but their KHE secret. So their KHE secret is short, small, independent of the input length. So this gives us a committee that's independent of the client input length. So the basic workflow is the following. We have the client, they just, once the client go online, then they submit their input, encrypted contributions, and the server collect all those contributions and aggregate the ciphertexts. Then the server send the EHE ciphertext to the committee. The committee help the server to learn the aggregated KHE secret. Then the server can just decrypt the aggregated KHE secret key and learn the aggregate. So this is the outline of the Willow protocol. Next, I'm going to show you how we build a secure protocol. So I'm going to start with the simpler case where the client, the server is semi-honest, but the client could be malicious. So in Velo, we use RingRW-based KHE. In particular, the RingRW-based homomorphic encryption schemes has very fast encryption and decryption. And because we only use additive homomorphism, so the homomorphic addition is really, really cheap. In Velo, we also use small Gaussian secret. This is to help so that the AHE cost can be minimized. But at the same time, to build a secure protocol, we need to notice that the server learns the sum of the KHE secret, and also the server learns the sum of the KHE errors. So this is like an inherent issue in the lattice-based crypto. In order to achieve confidentiality of individual client inputs, we rely on the new hint RingRW assumption, which essentially says that if you use slightly larger Gaussian parameters, and this protocol, and we can give out the sum of the secret and also the sum of the errors, and the security is essentially equivalent to standard RWE. So in practice, we can set the error parameters should be just 4.5, slightly larger than the typical 3.2 you would use. And so we use slightly larger, but still small parameters to achieve security. Well, this is only to achieve like a typically passive security, but we have malicious clients. So in particular, because homomorphic encryption is naturally malleable, it's subject to a whole sequence of attacks. For example, this correlated ciphertext attack. And in this attack, the adversary can just corrupt one client, and the adversary at the same time corrupt the server. So with those, and then the adversary will be able to set up the malicious client so that the malicious client input contribution will just cancel the honest client AHE ciphertext. So this let the adversary learn, in particular, this let the adversary learn this honest client input. So in order to prevent those kind of attack, we add a zero knowledge proof in our protocol to build a secure protocol. So let me show you some details. In Velo, we also use RingRW-based AHE scheme. And you can think of the typical parameters that each AHE ciphertext has two polynomials with about 4,000 coefficient and 70 bits modulus. In order to prevent this correlated ciphertext attack, we ask all the clients to prove that their AHE ciphertext is well-formed. So in particular, this is to give a zero knowledge proof of knowledge of the private elements used in their AHE encryptions. How many time do I have?
You still have 5 minutes.
Okay, I'll be very quick in the following. So the question now is what proof system to use. So in our protocol, we want to support weak clients, and also we don't want any setup assumptions. So this means that our proof system should be really efficient in terms of proof generation and also the proof size. At the same time, we want to support a large number of clients so that we want the proof system, the verifier, to be kind of efficient. Ideally, there could be some batch verification optimization. So with this, we choose bullet proofs, and we take advantage of the structural property of the RingRW encryptions. We reduce essentially RingRW encryption is like a linear relationship, so you can reduce the proof of the ZK proof in our work to a big inner product proof. So specifically, some very detailed work we need to take care of is, for example, the first thing is the different moduli in the RingRW scheme and the group size we use in bullet proofs. And this is essentially we're gonna leave the RingRW equation to the integers and prove and add some approximate range proof to show that this relationship still holds in the group. And at the same time, we use another approximate range proof to show that the error is small. So the detailed technique is pretty similar to the armadillo in the previous talk. And also they all come from this work from Eurocrypt 2022. And so let me show you some benchmarks. In our work, we choose the AIG parameters, which essentially is good for up to billion client. And as you can see from this this diagram, the encryption part for the client is really cheap, and the prover time, the ZK proof part for the client is also not very expensive. It's under 2 seconds to generate. And one particular property is that the proof can be generated offline because the proof doesn't depend on the input. And as for the verification, the server only does under half of seconds to verify each of the client's work. Also, there as for the decryptor for the committee, we're going to require 2 additional very similar proofs. So their proof cost is pretty similar to the client's proof cost, and also the verifier cost for the server is also pretty similar. So this is for the semi-honest server version of our protocol. And I'll skip the communication. As for the malicious protocol, so in the malicious case, malicious server the malicious server can arbitrarily aggregate the client, or can arbitrarily produce the aggregated ciphertext. So in order to prevent malicious server attack, we ask the server to generate a proof of the correct aggregation. In particular, this proof contains no confidential information, so the verification can be distributed to a small set of committee, so that each verifier only does a fraction of sublinear fraction of the verification work. So to conclude, we have a new secret aggregation protocol with one-shot client, and we support malicious server and malicious client. And our proof is we give a simulation-based proof in the random oracle model. And one additional property is nice property. We shown that it's impossible to achieve sublinear communication once the client submit their input. So it's impossible to achieve sublinear communication in the standard model if for the committee, between the committee and the server. And there are a couple of open questions still remaining. In particular, in our malicious server protocol, the verifier needs to repeat the server verification work. So it would be nice if we can improve our proof system to give kind of like a proof of verification, so that the verifier can only just verify the server generate the proofs correctly. So with that, I'd like to finish my talk, and I'll take questions.
Any question? Yeah. Oh, you mean the committee size? Yeah. I think for this, we do not assume the size of the committee. But the cost is like for a single committee member. Yeah. So we have one question from online. So Antigone, do you need a setup for the threshold homomorphic encryption? Yes. So I think it's like one round, because every committee member, they can just submit their key shares, and the server aggregate the key shares to get the key pairs. Yeah. So that's the simple setup we use. Yes.
I think we set our parameters so that maybe like up to 1 billion clients, but we can definitely just increase. For example, we can just increase the AHE's parameters slightly to support even larger number of clients. Yeah. Sure. Yeah.
In your protocol, you say that the additive homomorphic encryption is independent of the input size, but the input to the additive homomorphic encryption is the symmetric keys.
Yeah. Yeah.
Which, I mean, if you're using one-time time, it could be as long as the input, unless you use a PRG trick.
Yes, we use the PRG trick. Yeah. Yeah. Thank you.
Okay. So if there's no more question, let's thank the speaker again, and let's thank all the speakers in the session. So since we are behind the schedule,